Thank you, Dan. Welcome everyone to this seminar. There's been a tremendous interest in this. I hear we have over 10,000 sites, including Mars and Venus, have signed up for this seminar. But welcome. Today we were going to have our annual partner event, but to reinforce your stereotypes about Troy, New York, we had 2 to 3 feet of snow yesterday, and so we had to postpone our event. But the troopers have come in, and we're here today to try to reduce your uncertainty about what is a very hot topic. I want to first of all thank our partners and our sponsors that really make this possible. Mariana and I wrote a report last June in response to the publication from AMA, and it continues to hold a lot of interest. But it's our partners and sponsors that really enable us to have the time and research necessary to try to provide what we hope is a credible response. I also want to acknowledge our sponsors, the National Institutes of Health, the U.S. Navy, General Service Administration, government sponsors that also provide a great deal of support to us to enable us to meet our mission. Now, before we talk about, if you will, the collateral effects of light, which is the main topic today, I think that it helps for us to start with an orientation with a simple question: why do we light? We're certainly not trying to cause problems by providing illumination indoor and outdoor environments. But we have, in principle, a series of functions that we expect out of our lighting system. And part of the research that we've been doing, Dan alluded to at the introduction, is to try to quantify how light impacts visual performance, safety, sense of security, and quality of life. In the lower right corner, what you see is a complex set of functions that represent different ways that the visual system processes optical radiation on the retina. So for example, V lambda is the curve that represents how well we see or we can thread a needle, all the way to issues of the non-visual effects with the circadian. I want to draw your attention to the shaded region here, which really represents the full range of sensitivity of the human retina to optical radiation. And what you'll see as I go through this is how different parts of the retina convert that into different neural signals. So I think that going back literally over 100 years, the primary consideration for lighting is for visual tasks like assembly, reading, and accounting. Those are still remain a central part of the purpose of lighting, as well as how we tend to specify lighting and write recommendations. But it also is there, we provide roadway lighting, both headlights and street lights, for what we call crash avoidance. People are going to use their fovea generally to be able to judge, for example, a car coming at us. If you just see the headlights, you don't necessarily know its direction or its velocity. So street lighting provides that figure ground information that is represented here by this surface of relative visual performance, the so-called plateau and escarpment, represented spectrally by the V lambda function, again within a subset of the entire spectral sensitivity of the visual system. But driving is more than on-axis vision, so if I want to see this bicyclist while I'm looking down the road, what you see is that a different part of the retina and brain are processing that simultaneously while you're judging speed and velocity of objects in front of you. So this is a research study out of our laboratory showing how luminance measured with the photopic luminous efficiency function for high pressure sodium metal halide increases in that plateau region, showing that it really doesn't matter for on-axis whether you're looking or you have a roadway illuminated by metal halide or high pressure sodium. But detecting that bicycle in the periphery makes a big difference, and understanding how we can take this science or research into and apply that becomes very practical. So we are lighting for safety, and we have a great deal of knowledge now that allows us to do that appropriately. In fact, we have a computational model that allows us to look at the full range from starlight to daytime conditions and how the spectral sensitivity of the eye changes with a matter of light level and, of course, where it is on the retina. But we also light for people to feel safe. This is a project recently sponsored by Bonneville Power Administration at the University of Washington. It just so happened they have some parking lots to support nighttime classes, and one was lighted in high pressure sodium, one in metal halide, and one in LED. We drove people around in a bus and we asked them to evaluate it. And what you have here is looking at how safe people feel as a function of illuminance. And what you see is not a very good correlation if you use that spectral weighting function. But if you plot it as a function of brightness, which is a different channel in the visual system, you get a very nice positive correlation. The point being of all this is that we want to be able to quantify the impacts of the visual system has with regard to different spectra and amount of light. That becomes critical in the discussion that we're going to talk about today. Mariana, when she gets up, will talk about another reason, sort of the newest reason, if you will, that we light, and that's to improve the quality of light. What we see here again is the envelope for sensitivity of the eye to optical radiation, and these two curves represent how the human circadian system is going to process that light. But if you do it properly, you get better sleep, less depression, and reduced agitation. These are the kinds of things that we've been pioneering here to try to translate the science into applications. And as I said, Shu will talk more about that in the future. Now, all those good things, and I don't think anyone would disagree, those are bad things for us to do, performance, non-visual effects, and so on. But they can have negative collateral impacts. And the ones that were discussed in the AMA report were these three. Blindness from blue light hazard. And what you see here is a retina of a macaque monkey that has been exposed to very bright blue points of light. And what you may not be able to see are the small amounts of bleaching. At those points, that retina is completely blind. So we do have to be concerned with how we deliver light to the retina. I think everybody is at least qualitatively aware of glare. People are going to have two types that have been discussed in the literature for at least 60 years, disability and discomfort glare. And then we're going to talk about the other potential negative impact, which is circadian disruption or nocturnal melatonin suppression. And what we see here is a paper that we did, a photograph from a paper we did looking at LED-based tablets that we can measure how much melatonin is suppressed during the nighttime. Now, before we start, I'd like for you to keep in mind a quote from Albert Einstein. And he said that everything should be made as simple as possible, but not simpler. I think that we're here today to talk about some complexities. We will try to get it down to the simplest possible communication, but you can't oversimplify these things. So we consider out-of-bounds discussions of blue wavelengths and even correlated color temperature. These are too simple to really reduce your uncertainty with regard to how optical radiation on the retina might affect these collateral negative effects. You also have to always remember the use cases. Before you can make a meaningful statement about risk, you need to know how people are being exposed, both the amount and duration of light on the retina. Now, I show this picture of the solar eclipse, which was really the first time I think it was brought to the attention of the medical community of why people became blind, blue light hazard in particular. Prolonged exposures to very bright light sources can indeed cause permanent blindness in people. And it was really the solar eclipse that gave an indication that this was something that had to be addressed quite apart from the traditional way of thinking about light's effect on humans. Let's see. Not quite sure why we're not doing that. So what is blue light hazard? It's permanent or temporary. Sometimes you can recover from this. Loss of visual photoreceptor function followed exposure to short wavelength radiation imaged on the retina. And what you have here is, again, this visual sensitivity envelope in gray. This is our way of normally measuring light in the photopic luminous efficiency function. This dotted line is the blue light hazard function. And you'll notice it actually extends into the region of the retina that goes beyond visual sensitivity and can cause damage in the near ultraviolet as well. Now, the cause of blue light hazard is one that deals primarily with photochemical changes in the relationship between the photoreceptors and the pigment epithelium. This is inverted retina, light coming through the pupil, filters through the neurons here, and then is absorbed by the photoreceptors, which point away from the pupil. But it's the pigment epithelium here that is, first of all, a black substance in the human eye that reduces scattered light, but it also serves as the blood-brain barrier to the retina being part of the brain, in fact. But it also has to do, primarily in the context of blue light hazard, with the regenerative processes that take the nutrition, convert it into photopigments that then are recycled through the pigment epithelium. And it's this exposure to bright blue light imaged on the retina that is actually causing the permanent or at least temporary damage. Now, one of the concepts I want to get across here is that irradiance at the eye is not normally what you want to measure when it comes to assessing the blue light hazard. So in principle, well, in this example, what you have is exactly the same illuminance or irradiance at the cornea, but very different degrees of blue light hazard. If I have a large extended source that's imaged on the retina for the same illuminance as the other, there is no risk of blue light hazard. So the blue sky is blue, but it's a large extended source, so it does not represent anything that one should be concerned with. There's a lot of irradiance of blue light at the cornea, but it's because it's an extended source, does not have potential for damage. The worst possible case is when you have a very small point of light, like that picture I had of the retina of a monkey, is imaged at a point here. The illuminance at the retina, at the cornea, is the same, but the radiance from the light source imaged on the retina becomes the critical consideration. Now, the standards are written around a notion that the eye is constantly moving, either through microsaccades or inversion of glances, and time becomes another critical consideration because the eye is constantly moving. So this would be fixated on the retina artificially, but in the natural condition, that small point of light represents an area on the retina. So you have to think in terms not just of the radiance of the source, but the time-dependent variation across the retina that becomes important. But the primary metric you want to consider is radiance of the light source. So what we've done is we've done some calculations with different types of light sources that you see here. These would be ones that one might commonly experience. And then we have here the actual luminance, the effective luminance. So remember, again, very small objects will have an effective luminance less because they're constantly moving across the retina. A large source will stay in principle imaged at the same point on the retina. So the size of the object becomes important as well. Then you have the blue hazard weighted radiance, which is comparable to luminance, but now has that dotted line to weight the spectrum. That's in this column. And then what you end up with, according to the CIE IEC standard, a permissible exposure time for viewing a source. Now, the worst source from the point of view of blue light hazard one can experience is the noontime sun. And you should not look at it for more than 1 second. And remember what I said before about eclipses. It drops the radiance down because it's blocking the main part of the sun, but can also have high radiance. If you look at it for more than a second, you do run the risk of blue light hazard. But what I've done in here and highlight is highlighted 4 types of blue sources. I have already mentioned the blue sky, and the exposure time is in 24 hours, 44 hours, so that being longer than a day, certainly longer than daytime, which is normally 12 hours. This represents no hazard. A blue LED light box, of the kind that you might have for phototherapy, for example, is still very long. One can look at this a fairly long amount of time before you begin to even worry about blue light hazard. So 4.6 hours is quite a long period of time. But when you come to a single LED dye, 6 minutes is getting close to where you might want to be really concerned about that. It's small, it's averaged across a certain part of the retina, but it still represents, I consider, to be a potential hazard. But remember, you have to stare at it for about 6 minutes, which most people would probably not do. We've picked another one here, which might be the worst case. It's that we know of. It's a blue LED, high-powered, and we're looking at about a minute. So a second for the sun, about a minute for an LED, based upon the IEC CIE recommendation. Now, since the AMA brought particular attention to 3,000 and 4,000 K white LEDs, we picked 2 examples. There are many that we could have picked, but we picked 2 examples, what we consider to be representative. And again, these are small sources, but according to the calculation, you can look at it for about a half an hour. Somebody in the laboratory might do that, but I think it would be unusual for anybody to actually spend their time looking at a small dye from either 3,000 or 4,000 K LEDs. So this is quite a while, and again, what I've said at the beginning, we have to begin to think about use cases. So most people are photophobic. Many ways to deal with it. You've got sunglasses, hats, you shade your eyes, and so on. But there are use cases, and I'll talk about that in a minute, for seniors who have had cataract surgery, potentially premature infants. That's why they tend to want to cover their eyes, because they may not have a photophobic reaction. So a long-term exposure to a premature infant may in fact be a risk. And one of the ones that, as we put this together, that I hadn't considered is actors who must not appear to squint or shade their eyes when they are addressing an audience. So one has to be potentially concerned if you're going to do Shakespeare in the Park at night with spotlights. Now, I wanted to again bring your attention to the seniors. This is a common surgery. You have a cataract that forms in the crystalline lens of the eye. It's then replaced with a prosthetic, and you have what's called an aphakic lens that is put in. Now, I believe that most ophthalmologists today would not have a aphakic lens that would represent the spectral transmission of this curve. Most of them are now using yellow tint specifically to protect blue light hazard. But we've taken this curve to show you that ultraviolet radiation can in fact be a problem for people that have had cataract surgery with a replaced lens, if its transmission characteristics are the kind that we see in this graph here. So what we've done is we have, in parentheses, compared, if you will, the normal lens with the aphakic lens. And what you see is, for viewing the sun, remember it was about 1 second, you're cutting it a little more than half by having the ultraviolet radiation from the sun that's now going to reach the retina. So now what was a second is now a half a second. One of the most dangerous, I'll say, light sources we have is an incandescent filament. Most people feel that at 2800 K you don't have a risk, but in fact there is radiation in short wavelengths that can cause blue light hazard. So we had about 20 minutes exposure before. That's been cut to 10 now for people that would have a aphakic lens replacement. But I want to point out that it makes no difference to an older person with a phakic lens for an LED. There is no additional energy in that short wavelength region. So it was 33 minutes for the 4000K to start with. It remains 33 minutes even for a lens replacement. So you need to know the spectral power distribution as well as the transmission characteristics to the eye before you can properly assess blue light hazard. So in summary, spectrum matters. And you've seen this curve that show white LED and they say, oh my gosh, it's right in the middle of blue light hazard. But it doesn't matter nearly as much as optics. Remember, it's the radiance of the source that is critical. And even an incandescent source with very little radiation in this region is the most dangerous light source commonly available today, notwithstanding the sun, of course. So you need to understand that it's the radiance and the spectral power distribution, which is both spectrum and amount, that has to be considered in your assessment. And as I mentioned, use case matters. Most people exhibit photophobia, but there are indeed special populations that do need consideration. Newborns, phakic lens replacement individuals, and actors. These are the kinds of people that are going to have prolonged viewing. And I should add to this, industry scientists working in LEDs that spend a lot of time looking at them while they're operating is another case where this could indeed be a significant issue. But use cases do matter. Now let's talk about glare. This is a very old topic. AMA brought it up, maybe surprisingly, because we've known about disability glare since one of the actual people on my thesis committee, Glenn Fry, published in 1954. That was before I was born. But nevertheless, you do have to consider disability glare, which is the reduction in visibility. And you've all experienced it at night, whether we have headlights coming at it. You cannot see the roadway anymore. And discomfort glare, which is quite a bit different. It has to do with how uncomfortable that light source actually is. And recently, our colleague, Dr. John Bullough, and other people here at the Lighting Research Center have been working on this problem, and I think we have a pretty good understanding now with the work that he's done on how to be able to predict discomfort glare as well as disability glare, which again has been around for quite a while. I drew this chart, I didn't draw this chart, I am presenting this chart to show you the kinds of differences between disability glare. So imagine this person viewing this line of sight, and we have 3 independently operated incandescent 100-watt lights above on the ceiling, an 8-foot ceiling. And what you see, maybe surprisingly, the first one causes less disability glare because of the angle than the ones at 2 and 3. So you see an increase as you move from that glare source to that glare source to this glare source. Now, if you ask this person to look in turn at each of those 3 light sources, the one that produces the least discomfort glare is this one. So one of the points I want to get across is that it isn't seen as believing. You have to do the calculations to reach a valid inference. As discomfort glare is going down, disability glare is going up. So you need to make sure that when you're talking about glare, you need to make sure that you're talking about disability glare, what are the dynamics of that, as opposed to discomfort glare. Now, to show you some of the research that John's been involved in, this is disability glare plots, and it shows that for 2 angular distances, 5 degrees and 10 degrees, this being 10 and this being 5, that the spectrum really doesn't matter. It has to do with how much light you have and the angular dimensions between your line of sight and the angle of the light source, the glare source from that. But this is what's going to reduce visual performance, the readability, if you will, acuity, contrast threshold, reaction times. But the spectrum does not matter. It has to do with the V lambda, foveal spectral sensitivity, and scattered light is scattered light. These are large particles that are going to be scattered in the lens primarily, but other parts of the optical media. So that scattered light is insensitive to the wavelength that is scattered. The scatter is independent of the wavelength. Discomfort glare is different. This scale, to just throw you off a little bit, as you go down on this, that means more discomfort, not less. So you're increasing the illuminance, photopic illuminance at the eye. And now we're going to take narrowband sources and we're going to ask people, how uncomfortable do you feel? And you can see here what the standout is the 450 nanometer source. So this is the more apparently glaring source, discomfort glare. As you increase illuminance, discomfort glare increases, and you start off and continue to be worse for blue light than you do, say, for red or yellow. Now, what is underlying that is, again, this is the envelope. We're taking the cones, the 3 cone types, putting them together into this calculation procedure. And what you see is that if you take this function and you apply it to the spectra that we just saw, all of those points lie on a single line. So we're able now to predict discomfort glare, and spectrum does matter. Okay, so that is a critical issue for how uncomfortable one feels. But in terms of disability glare, just because you're less comfortable does not necessarily mean your ability to see has become worse. Remember, those are different. So here's the summary for our glare. Photopic illuminance at the eye matters. How much radiation is at the cornea? The angle from the light source matters. And so in both of those, that's true. The dynamics are slightly different. But for the luminance of the source, the spectral power distribution, and the psychological factors, all of those impact discomfort glare. And by this one, when I say psychological factor, if it's a harder task that you're doing and you ask somebody to rate it, they invariably rate it as more uncomfortable for the glare source. If you're, for example, as we were yesterday driving in snow, that becomes discomfort glare becomes more attuned. But the point is, these factors are not important to disability glare. So again, if you're going to make statements about the impact that light is going to have, we have to know the difference between discomfort glare, disability glare, and we have to be able to do the quantities in such a way that we can come up with a meaningful answer. Remember, keep it simple, but not too simple. So I'm going to turn this over now to Mariana, who will then talk to you about the circadian effects.
Good afternoon, everyone. I am going to talk about the third area that the AMA addressed in their report, which was the light's effects on circadian system. We know that circadian rhythms are biological processes that repeat every 24 hours or approximately every 24 hours. These are called circadian rhythms. Circ is about, or approximately, D is a day. Circadian rhythms, they are generated and regulated by a biological clock in the brain. In humans, circadian rhythms are going to free run with a period slightly greater than 24 hours. In other words, if you're in a dark cave without external cues, you're going to continue to have circadian rhythms. The difference is that these rhythms are going to run with a period slightly greater than 24 hours. So every day you would be out of sync with your watch. So light on the retina is the primary synchronizer of circadian rhythms to the local position on Earth. So every day, more specifically, every day when you wake up in the morning, you get light. That light will reset or re-entrain your biological clock so that it's running with a period of exactly 24 hours rather than 24.2 hours. So it allows you to wake up at 8 o'clock because your biological clock is telling you that it's 8 o'clock in the morning. However, lack of that light during the day, especially morning light, or too much light in the evening or in the middle of the night when we're supposed to be in darkness, can also be a major disruptor. And we know that disruption of circadian rhythms has been associated with a series of maladies and diseases, including poor sleep, poor performance, and high stress, all the way down to higher risk for cardiovascular disease, type 2 diabetes, and even higher incidence of cancer. And a lot of the work with cancer, and more specifically with breast cancer, has been done with shift workers who are known to suffer a lot of circadian disruption. Now, light can also have an acute effect on humans. So one of the very well-known markers of the circadian clock is melatonin. Melatonin is a hormone that it's produced at night and in darkness. So if you're in a dark room in the middle of the day, you're not going to produce melatonin. If you're in a very bright room in the middle of the night, you're also not going to produce melatonin because light can suppress melatonin. Now, melatonin is a very important hormone. It is, first of all, a timing messenger to the body. So it tells the body that it's time to go to sleep in the case of diurnal species, or it's time to be active in the case of nocturnal species. It's always high at night and low during the day. Melatonin also has been shown to have oncostatic effects. Using animal studies, a lot of work done by David Blask and colleagues show that if you remove the pineal gland from the animals, these animals cannot produce melatonin. If you inject a tumor in the animals and you give them exogenous melatonin through injection, this exogenous melatonin will reduce the growth rate of tumors compared to those that do not have high levels of melatonin. And as I mentioned, light can have this acute suppressing effect on melatonin production. Light can also phase shifting the timing in which you start producing melatonin in the evening. So if it delays, if you get too much light in the evening, you're going to delay that dim light melatonin onset. By delaying the dim light melatonin onset, you delay that signal that it's time to go to sleep. And obviously all of us have a very set wake-up time. We end up curtailing sleep, and we know that curtailing sleep has also been associated with a series of maladies. Now, we do know from work that has been done that short wavelength light with a peak at around 460 nanometers is maximally effective at suppressing melatonin or phase shifting the time of melatonin onset in the evening. So given that light has this very strong effect, either an acute effect or a phase shifting or circadian, the potential for the circadian disruption, we'll obviously have to be concerned about light at night exposure and health. And that started in the 80s with the melatonin hypothesis. Richard Stevens from the University of Connecticut put forward the hypothesis that the suppression of melatonin by light at night and by electromagnetic fields was hypothesized to increase the production of estrogens in the ovaries, which in turn would stimulate the turnover of breast epithelial stem cells. So in other words, a person is exposed to light at night, that light at night suppresses melatonin, that results in increase in estrogen levels in the body, that increase in estrogen levels in the body can then lead to increase in breast cancer or breast cancer risk at least. I think with a lot of the work that has been done since the time this hypothesis has been postulated, people are moving more towards the circadian disruption hypothesis, which could or could not involve acute melatonin suppression. So I think the circadian disruption is a little bit more general hypothesis, and that hypothesis doesn't include only breast cancer, but it also includes other diseases such as the ones I talked about in the previous slides. So obviously, if lighting is so important in minimizing acute melatonin suppression or circadian disruption by light at night is so important, we obviously need to understand what kind of light will affect the circadian system. So starting with the basics, circadian phototransduction, which is how the retina converts light signals into electrical signals for the biological clock in the brain. We do know now that we have a novel class of photoreceptor. I mean, it's not as novel because it's over 10 years now, but it's more novel than the classical photoreceptors, rods and cones. This really work that started with Russell Foster in the 90s, where he showed that genetically manipulated mice that were basically blind, they had no functional rods and cones. He would give them a pulse of light, and they would, the following cycle, they would change the timing of their wheel running activity, suggesting that there was something that was responding to that light for the circadian system, because wheel running activity is sort of a marker for circadian rhythm activity in nocturnal animals. He then removed the eyes and nothing happened. So clearly there was something inside the eyes that was responding to that light. Then in 2002, David Burson from Brown University discovered that novel class of photoreceptor, the IPRGCs, or intrinsically photosensitive retinal ganglion cells. They are located in the ganglion cell layer. They have a peak sensitivity at about 400 to 484 nanometers. I do want to point out that that peak sensitivity is longer than the peak sensitivity for acute melatonin suppression, which is close to 460 nanometers. And obviously, I'll tell you in a minute why. It's because the IPRGCs do receive processed information, including spectral potency, from the classical photoreceptors and then transduce that information to the brain. So if you look at the graphic here, that's a cross-section of the retina. This is how the light comes through. This is the ganglion cell layer where the IPRGCs are located. Light goes through all these, gets into the photoreceptor layer, which is where the rods and cones are located. The rods and cones will absorb the photons, and then these photons are going to be processed here in these layers of the retina, including the bipolar layer where spectral potency is formed. Spectral potency are the two color channels that we have in the brain, the B minus Y, which is blue minus yellow, and the R minus G, which is red minus green. And those are, as the name says, they are opponents. So the B subtracts from the Y and the R subtracts from the G. So there's a subtraction, and then the net result is given, it's passed on to the IPRGCs and the regular retinal ganglion cells. The regular retinal ganglion cells goes to the brain, to the LGN for color information, but you also have the IPRGCs that receive that information and transfer it to the biological clock. So consistent with that, a lot of studies were done right after the discovery of the new photoreceptors. And now the whole field agrees that all 5 photoreceptors, rods, the 3 types of cones, and the IPRGCs participate in circadian phototransduction. Now, what's very interesting is that we do need the IPRGCs to be able to transduce that signal to the brain. But we don't need melanopsin. If you remove melanopsin from the IPRGCs and you keep the IPRGCs in the retina, you still have some, albeit diminished, response by the circadian system. And that response is sort of a result of the processed information that comes from the rods and cones. So we do know that we need all 5 photoreceptors. The question is, how are they combined in the retina to respond to light for the circadian system? So that's part of the work that we've been doing here. We've been proposing a computational model, and Mark Rea has led that effort here, which our model is constrained by the known photopigments, so the 5 photoreceptors participate, and also by the neuroanatomy and neurophysiology of the retina. So therefore, we do take into account the spectral component that occur at the bipolar levels, and that information is then passed on to the biological clock in the brain through the IPRGCs. So here is just the formula. In case they didn't tell you, we're going to have a quiz at the end, and you're going to have to sort of tell me about the formula. But the intent is not for you to remember that, other than there are 2 equations there, and the 2 equations, the equation on the top, which is the long equation, is typically for light sources that tend to have a B greater than a Y. So in other words, light sources that tend to look more cooler. The equation in the bottom is when you have a warmer light source that ends up being, in fact, just the melanopsin response. And through this model, using the spectral power distribution and the light level, we can then calculate what we call circadian light. Okay? But circadian light is really the stimulus. It's what reaches the photoreceptors, and this is how we think they are absorbed and processed by the photoreceptors. But we wanted to go a step further and talk about a response by the circadian system. And in that case, we looked at a transfer function between the light stimulus, which would be circadian light, and the circadian response, which would be acute melatonin suppression after 1 hour exposure. So that's our definition of response by the circadian system. This is not the only response by the circadian system. It's only one, but at least it's better than not having a response and not knowing what threshold and saturation is. So here is putting those 2 ideas together. We have the spectral sensitivity here on this graph, where you have 2 functions. One would be when this is a function when your B is greater than your Y, so it would be more for cooler light sources. This is a function where your B is less than your Y, and that you would be more for warmer color light sources, and that's really a pure melanopsin response in that case. And this is your phototopic luminance efficiency function, so clearly you see that lux levels are not the right units to be used for circadian system. And then here is the absolute sensitivity, which is using that transfer function. All these points that you see on the graph here are points from studies that have been published on acute meltdown suppression in the literature. And as you can see, this is your outdoor nightlight level, so you're pretty much very close or below threshold. And then you have indoor homes here, indoor offices, and then you have outdoors, which pretty much are saturation. So above 1,000 lux and so on at the eyes, you're pretty much above saturation. So obviously every time you put forward a model, you want to be able to validate the model, and then if there's something wrong, go back and fix it or adjust the model. So we did do field studies validation. I don't have time to talk about that, and it's not even part of this talk, but we've been working with Alzheimer's patients, submariners, kids in schools, and we're seeing that circadian stimulus metric is a good metric for predicting some health outcomes. But in terms of laboratory studies and looking at acute meltdown suppression, we did a study where we looked at 2 CCTs, or correlated color temperature. Now, I do want to point out CCT is the wrong metric, and I'll tell you in a minute why, but that's what everybody's used to it. Same thing with a graph where I have the lux levels, which is the wrong unit, but at least as a translation for us to have an idea. So these is the spectral power distribution of the warm color source, and this is the spectral power distribution of the cool color source. And these were the light levels that we ran. Here are the data that we collected. These are acute meltdown suppression on the y-axis, and these are the different studies that we did. Now the standard deviation are variations, so there's a lot of individual differences in how people respond to light without any question. And these are model predictions. This is not a curve fit to the data. This is our a priori predictions. This is what we predicted that we were going to get, and we were getting very close to our predictions using the model. So we then developed this circadian stimulus calculator that's available online for anyone to download. It's a simple metric where you put the spectral power distribution, you put the light level at the eye, and then you can calculate the circadian light and the circadian stimulus. And here there's a little graphic that gives you whether you have a B greater than the Y or B less than the Y. So what function are you using to calculate your circadian stimulus? Now, again, this is for comparing the effectiveness of different light sources. You do need to input the spectral power distribution, and you need to input the light level at the eye. Those are the 2 pieces of information that you need. So here are one of the reasons why we think that correlated color temperature is not the right metric when you're talking about acute meltdown suppression. So here we got in the y-axis, this is circadian light. We actually normalized it to a photopic illuminance at 300 lux at 2856. And here are the CCTs in the x-axis. And you can see here, there is this intransitivity here. And what this intransitivity is, it's really what side of the B minus Y channel you are. If you are on the warm side, you actually have a reduction in the response. Why? Because it's B minus Y. You're subtracting something from the blue, and you get that response. If you are on the warm side, you just have a melanopsin response. That also has some threshold associated with rod response, but I don't have time to get into a lot of details. But what you see here, this would be if you're using melanopic only, and a lot of people are talking about melanopic lux, this is also the wrong metric because you're using melanopic only, and it is overestimating for certain spectral power distributions the effect of that light source on the circadian system. Okay? If you go to very, very short wavelengths, close to 440, 450 nanometers, then the melanopic only would be underestimating. So again, that underscores the importance of looking at the SPD and not just relying on correlated color temperature. So applying that, using circadian stimulus for outdoor lighting applications, and in response to what the American Medical Association said that you should use only 3000 K, here's an example where you could use a 4000 K light source and you would have less circadian light from that light source than you would have with a 3000 K. So these are the two spectral power distributions of the two light sources. We ran it through the model, and we obviously, in terms of lux levels, they're about the same. So, there's no difference. But in terms of the circadian light, the 4000 K is much less effective for the circadian system than the 3000 K. So it could be that you are specifying a 3000 K and you're actually giving a greater stimulus than if you would have been using a 4000 K, for example. Okay, and this is why this happens. It happens because some of the SPDs around this range, between 3 and 4000 K, will fall into this area here. And what that is basically is, depending on the SPD that you get, you can get it either on this side or on this side. So in the case that we showed before, you have a CCT of 3000 K, a CCT of 4000 K, but the 4000 falls on the other side of your B minus Y, so it becomes less effective for the circadian system. Now, there are SPDs, 4000 K SPDs, that could have a higher circadian lighting than a 3000 K SPD. So the bottom line here is CCT is not a good metric because you don't really know what side you're falling, and you don't really know what that response would be. So you need to get the spectral power distribution and do the calculations before you can say anything. So just to put that example into perspective with the IS recommendations. So what the IS does, the IS only recommends the light levels, and pretty much it recommends the horizontal light levels. So we estimated that it would be about 18 lux at the eye of somebody sitting under this pole here. This person would be getting about 18 lux at the eye. So if you look at the transfer function here, where 18 lux at the eye of these light sources would fall, if you look at a high pressure sodium, for example, it would fall below, pretty much below threshold. It would have no impact on acute melatonin suppression after 1 hour exposure to that light. If you look at the 3000 K, it's a little bit more effective than the high pressure sodium, but it's also below threshold, or very close to being below threshold for acute melatonin suppression after the 1 hour exposure. And the 4000 K is even less effective than the 3000 K. So again, you need to know light levels, because if you only talk about spectrum and you're below threshold, it doesn't matter what spectrum you're using. You're below threshold, you're not going to have an effect. If you're up here, it doesn't matter what spectrum you're using, you're above saturation. So you need to know where you are in the operating part of the curve and what SPD you're using to be able to talk about circadian stimulus. So here is another example. This is for indoor environments, and we did the calculations using a 3000 K or a series of 3000 K LEDs and a series of 3500 K LEDs. Here you have the horizontal illuminance, so that would be the light levels on the work plane, which is what typically people measure. And we calculated what the circadian stimulus at the eye would be. And you can see that there's a lot of variation. I mean, even with different manufacturers, some manufacturers get to, say, a CS of 0.3, which would be halfway on that curve that I showed in the previous slide. Some manufacturers get it with 425, some manufacturers only need 375. So there's a variation depending on the SPD. Now what's interesting is the 3500 K light source, no manufacturers would get to that CS of 0.3 because it is less effective. So again, just to beat the dead horse, we do need to talk about spectral power distribution. We also need to talk about light levels. So the bottom lines for the health impacts from light is that you must consider all the physical attributes, the amount, the duration, the timing, and the spectrum, not just spectrum, okay? The same light that it's given you in the morning is beneficial. If given it in the middle of the night, is not going to be beneficial. So telling me what type of light and what amount of light without telling me when you're giving that light is also not beneficial. Get the metrics and the units right. Otherwise, there's no point in talking about the health effects of light. CCT is useless, and it's often actually misleading. Yes, you tend to have higher CCTs, more short wavelength content. They may be more effective, but it's not always the case. Photopic illuminance, and I think everybody agrees with that, has a very limited utility for characterizing how light stimulates the retina when it comes to the health effects. And as Mark mentioned, when assessing the risk, you must consider the use cases. Are you really going to be sitting underneath a luminaire for 1 hour outdoors? Maybe or maybe not. Certainly not in a day like today in Troy, New York, where it's 20 below zero with a wind chill. I wouldn't be there at all. So you have to make that assessment whether people are going to avoid that light or not. Okay. With that, I want to thank you, and I think Dan will be filtering out the questions that we can answer.
So Mark, why don't you get up there? Okay. Hopefully you can hear me reasonably loud. We did get a few questions. If anybody else does have questions, please feel free to type them into the question and answer box now. I'll start with the earlier questions. So these are from Mark. First question, what is the difference between actual and effective luminance?
This is with regard to blue light hazard. The effective luminance is for small sources that would be bright or high radiance. The assumption is the eye is constantly moving, so it kind of blurs out the real radiance to give you a lower average distribution. So when you have a small source, less than 0.63 degrees, you need to consider it not to be stabilized on the retina, but actually moving and averaging over different parts of that small part of the retina. When you have a large source, like the sun is a large source, even those small eye movements still leave part of a point on the retina exposed to high radiance. So when you have a larger source, you do need to take into account radiance. When you're talking about a small source, again less than 0.63 degrees, you have to take the time average across the retina to do the exposure limit.
Another question from Mark. Will suppression of short wavelength light decrease the consequences of light pollution into the sky?
That depends. It will, in a pristine sky, like in Arizona, for example, unquestionably the short wavelengths will be scattered more, just the same reason the sky is blue in the daytime. So indeed, short wavelength energy from an LED is going to scatter more in those pristine atmospheres. If, on the other hand, you're in Troy and you have high water content, for example, then spectrum becomes less important, and it depends upon whether you're observing the stars, the Milky Way, or individual stars, and so on. So yes, in pristine skies, short wavelengths matter, no question. In skies where you have high aerosol content, large particles, white clouds are white, for example, instead of blue, it doesn't really matter that much.
Okay, a question from Mariana from the beginning of your presentation. Why is our natural clock at 24.2 hours?
Well, diurnal species tend to have longer circadian clock, and nocturnal species tend to have shorter circadian clock. We think that there's a couple of reasons. First of all, you don't want to be exactly at 24 hours because you wouldn't have any flexibility. So having 24.2 hours gives you flexibility in terms of changes in day length and so on. But also the fact that we have longer, because when you wake up in the morning, you get light in the morning, that light will advance the clock. So what it's doing is you have a longer clock, it advances the clock, it helps you go back to 24 hours. In the evening, you delay the clock. So if you would be getting light in the evening, you need to have a clock that is shorter than 24 hours, and then you delay that clock to be at 24 hours. So you're starting your activity in the morning, you're getting that light that it's basically promoting entrainment, and you would have this longer clock that would promote that entrainment in the morning, and a shorter clock that would promote the entrainment with the light in the evening.
General question. Given the information presented, what SPD would you generally recommend for community street lighting?
Well, I don't mean to give you an overly glib answer, but I guess I'll give you one anyway. The cheapest one. I think that what the analysis that we showed today is you have a choice. it isn't a matter that 4,000 or 3,000 are really under the ways the IS recommends light levels and the expected use cases. It really is not going to be consequential whether you pick 4,000 or 3,000 K for the purpose of, say, melatonin suppression, which was the example given. But having said that, I mean, I think that we're doing research right now on more exotic spectra, where we could take a given, say, CCT, and we can either make it more or less impactful on the circadian system. So repeating, again, beating Mariana's dead horse one more time, CCT is not the right question, which you did not ask. You asked SPD. I underscore that, and I think if you use, for example, the calculator that's online for free, you can create your own spectra and determine what that effect is, or take a commercial SPD to do that. So spectrum and amount, duration, use cases, I think, gives you a lot of flexibility. So go cheap if you can.
Well, and I think that even the SPD that we show on the slides is a good SPD. The 4000K SPD is a good SPD because you don't have a lot of circadian stimulation. You're basically on the lowest there. So it really, I think that the beauty is nowadays you can actually play with the spectrum, and you can come up with a light source that will increase or decrease the circadian stimulation depending on what you want to do. And manufacturers have the ability to do that right now. So give them your wish list and have them give you the light source for that.
For Mariana, how would a lighting designer determine light level at the eye in practical applications? Is there a rule of thumb? Is there a more accurate way to do it?
Well, there's a couple ways. Obviously, you just put the illuminance meter here at the eye level, and that's fine. If you're doing AGI, there are vertical points that you can put on the AGI simulations. And rule of thumb is about if you have a recessed downlight, so a ceiling light, you probably have a ratio of 3 to 1 or 5 to 1. So if you have 500 lux on the work plane, you get a 3 or 5 to 1 ratio. You're going to have about 100, 150 lux at the eye. If you have more direct, indirect light sources, you get better ratios. So it's about a little bit over 2 to 1 ratio. So it really depends on the light distribution that you're using, but it varies between a 2 to 1 to a 5 to 1. But we did those lookup tables that I showed an example. Those are available online, and that was really for this purpose, because if you measure the horizontal illuminance, which is what are in the first column, you can then look up the table to figure out what the circadian stimulus at the eye would be. So that was the idea of doing that.
Yeah, just to add to that, the calculator which Mariana showed has the link. You would either take a physical measurement, or you could do photometrically accurate software, get the photopic illuminance at the eye, and if you know the spectral power distribution, you can determine the CS, which takes into account both spectrum and amount. So it's an add-on tool to what you would normally consider in your photopic illuminance design or measurement.
Practical question. Are SPD files readily available from manufacturers? Will we be building a shareable database?
Well, the calculator has some already. So when you have select SPD, we have some SPDs that we populated with it. But the answer to your question is yes. Ask the manufacturers. Manufacturers are very aware of that. Everybody now is making SPDs available. So that should be very easy to get it. If one manufacturer doesn't get, move to the other one. I'm sure somebody else will give you.
I want to add one other thing. When you come to an architectural application where you might have mixed light sources like daylight as well as LED, you do have to make some interpolation on what the effects are. But
we're doing a calculator on that.
Go ahead.
Now, I was just going to say, we are actually preparing a calculator on that, so it should be available soon, where you can have the percent from each light source, for example, daylight and electric light. So you can estimate what the percentage, and then the calculator will combine the SPD and give you a net result for that. So we are preparing that. We're about to launch that in the next few weeks.
Yeah, and just to be a little nerdy, you have to combine the SPDs before you do your calculation, not afterwards. So that's a small but nerdy point.
Have you found a basis for the 3000K recommendation that the AMA made? Is it just the assumption that a higher CCT equals more blue?
Yes, that's the argument. If you take, again, a qualitative assumption, there is more, it's a higher, relatively higher short wavelength peak for the 4000 than for the 3000. But as Mariana pointed out, you have to do your sums to determine whether that has a increased or decreased implication for that. So you can't just look at the qualitative curves and draw an inference, a valid inference based upon that. So yes, that is the argument, that it has more short wavelength content, therefore should suppress melatonin more, which is incorrect.
Is the LRC working to create a CS standard that can be published on manufacturer spec sheets?
Right now, we have the CS as a proposed metric. You know, we welcome anybody who wants to talk about standards. We really just want to give a tool to people to be able to compare different light sources and how effective they are for one aspect of the circadian system. I mean, this is really meant to give people a tool. Whether it's going to be a standard or not, as we all know, it's a long way until we get to standards. So rather than wait till the long wait, we're at least giving people a tool to be able to compare different effectiveness. Now, let me be clear. This is acute melatonin suppression. I'm not saying people are going to be smarter, produce more, win the lottery. We're not saying any of that. We're simply saying this is just one aspect of the circadian system, acute melatonin suppression. I think for the purpose of the AMA report, that was one of the reasons why they were limiting short wavelength content was acute melatonin suppression, because of the health effects associated with that. And all we're giving the specifiers and users is just a tool that they can compare different light sources and how it will affect the circadian system.
I'd like to add to augment what Mariana said a little bit. Remember that CS takes into account both spectrum and the amount, and I think that one has to consider both of those issues when it comes to a standard. But as Mariana said, it's still not complete, because a CS of, say, 0.3 in the morning has a very different consequence to a CS of 0.3 at 11 o'clock at night. So whatever standards are written around this, time and duration also need to be taken into account with regard to the circadian system. So it's a higher level of effort to get a standard that would be meaningful and helpful to people than it would be just illuminance for visibility. So remember, it's, as Mariana said in that slide, it's spectrum, amount, duration, and timing. All of those things would have to be in a standard to be useful, I think.
We'll take just one or two more questions, and then we'll end for the day. Can you explain how the CS metric differs from melanoptic lux?
Well, there's a few differences. First of all, as I showed in the presentation, melanoptic lux only takes into account the response of the IPRGC. It does not take into account the response of all other 4 photoreceptors. So that's one big difference, and I think the literature, many studies that have been done now agree that it's not just melanopsin, it's not just the IPRGCs, although the IPRGCs are needed to conduct that signal to the brain. So that's one main difference, and the CS takes into account all 5 photoreceptors, takes into account also the differences that the melanoptic lux, or which is the wrong unit to say melanoptic lux, but nevertheless that's what people use. It also does not take into account threshold and saturation like the CS does. So the CS does have the transfer function. So melanoptic lux would be how that light source is affecting only the melanopsin photoreceptor. That's it. That's what melanoptic lux gives you. It doesn't give you anything related to the response. So you don't have threshold to saturation, and you don't have you don't account for the response of the other photoreceptors.
Let's keep this as the last question. Would the LRC spectrum analysis tool work with dynamic spectrum Kelvin changing light fixtures?
If you can get the SPDs and you can insert the SPDs of the different dynamic changes, you can estimate that, especially now that we're going to be having a calculator that would be able to combine more than one spectra. But you still need the spectral power distribution and the light level to be able to calculate that.
Okay, I want to thank everybody for their attention and for joining us for the presentation. We've had many questions about whether we will share the slides from this. This has been recorded, and we will be placing the recorded webinar on our website within the next week or so. Obviously, we want to edit it to get out any problems that there were with sound and so on. But then we will be placing it on the website, so you will be able to view it at a later time. We will not send out the slides per se, but we will publish the webinar. So again, thank you all for joining us, and have a good rest of your day. Bye-bye.